I start this. So today you join me and Carlos for our webinar on water quality in the fish production. We will talk a bit more about why aquaculture and aquaponic systems heavily rely on the water quality, especially when it comes in consideration for health and productivity. So this webinar will explore the essential water parameters that must be monitored and maintained to ensure a thriving environment for all organisms in the system. However, we will focus on fish, while the parameters related to plants will be discussed in further webinars. So understanding these parameters is crucial for the disease prevention and promoting efficient growth. By end of this session, you will have a better understanding on how to monitor and manage these water parameters in your own systems. But first, few words about me and Carlos. So I'm a research associate at Zurich University of Applied Sciences, and mainly working on soilless technologies, on aquaponics, hydroponics, and bioponics, no matter if they come in low-tech or high-tech systems. And together with me today, we have Carlos, and I give word to Carlos to tell a bit more about himself.
Good morning, everyone. My name is Carlos Espinal. I'm one of the founders of Landing Aquaculture BV. Landing Aquaculture is an engineering firm based in the Netherlands. We are specialized in land-based aquaculture, of which recirculating aquaculture systems tends to be the most sought-after product and service that we offer. Myself, I'm interested in microbial dynamics, in recirculation systems, wastewater treatment applied to recirculation systems, and technology development, product development for this type of systems. Thanks.
And do you want to tell something about the company?
Sure. So, we started Landing Aquaculture about 10 years ago by Rob van de Ven and I, a friend of mine. We met working abroad for another company. Back in the day, we saw that there was a lot to improve in how these type of companies can deliver services to the market, to people that want to start fish farms. And we took it from there. We started as a small engineering firm, just doing feasibility studies and design studies for clients. And with time, people started asking us to do larger projects, to offer hardware, either from other manufacturers or fabricated by us. And since 6 years ago, we started a manufacturing workshop where we also design and manufacture equipment for recirculating systems. And after that, people then started asking us to solve problems that we didn't have solutions for. And from there, we started basically a small R&D department inside Landing, which pretty much started with me working with Zala in a few small research projects. And from there, we took it off as well. So now Landing offers a consulting and engineering service, fabrications and installation service, products. And at the same time, we are always involved in product development and R&D, sort of to look into more of the future of how RAS could look like.
Okay, so what's the plan for today? We will do a bit of introduction on aquaculture and water quality in general. Then we will do water parameters step by step, explore some different water sources and associated risks that you could use them to run your facilities. For the ones that would like to have the ELISA certificate, also some homework, and then the conclusions. So what's actually the water quality? Why is it so important, right? So everything depends on the water quality when we talk about RAS, if we talk about pond culture, if we talk hydroponics or aquaponic systems, right? Poor water quality can lead to stress, diseases, or even death of organisms. We can talk about fish, plants, and of course, the most importantly, microorganisms. which can severely affect the productivity of the system and at the end, our wallets, right? So bad water quality normally results in lower production. So maintaining this optimal water quality ensures the stable environment, so we have a good and thriving systems achieving maximum yields, right? But don't forget, for today, we will mostly focus how this water quality affects fish and bacteria, and the plants we will do later on. So what are the key water parameters that we will have a look at? We have different ones. One of the most important ones are the temperature, pH, dissolved oxygen, ammonia, nitrite, nitrate, salinity, and alkalinity. All these parameters play overall role in the performance of the system, and they should be kept in the safe ranges. And the most importantly, we also have to understand the interactions between different parameters and not just look at one parameter by its own, right? There are also other parameters such as other nutrients, algae contamination, solids, and so on that should be monitored. But in well-balanced systems, these parameters can be monitored less frequently, right? But you have to know your system well, especially if you would like to reduce the frequency of those measurements. For the sake of presentation, and because sometimes in English it's a bit confusing when we talk about nitrite and nitrate, I will stick to NO2 and NO3 over the presentation, that we always know what we are talking about. Carlos?
Yes, so I'm still stuck in a slide of landing aquaculture. So for some reason, I don't know why it hasn't updated to me.
Oh, I'm so sorry. Wait.
Let's check.
Works? Not?
No.
I try to stop share and I try to share again.
Yes, please.
Now?
No, I don't see it.
I see fine.
do
So it seems to be your end.
Seems to be on my end. Okay, let's do something. I will be running on the presentation on my computer, and then we know where we are. All right, here we go. Okay, now I'm running on the same slide as you are. Okay, so for starters, the first thing the most important principle in recirculating aquaculture, guys, is feed drives everything in the system. Feed addition drives pollution. Feed addition drives obviously growth, but it also drives the deterioration on the water quality, which you have to counter either with water exchanges or with filtration. How much filtration, how much water exchange depends on your project, depends on your location, how much water you have, etc. But the most important thing that you need to understand is that feed addition drives everything, which means that if you ever have a problem with water quality, the first action to take is to stop feeding and then think about the rest, okay? When you add feed in the water, you will see obviously within a few hours your solids accumulate and your water starts becoming cloudy. If you don't have anything to treat ammonia, it will start accumulating. Carbon dioxide accumulates very fast. And oxygen obviously is consumed very fast. The more feed you add, obviously the faster this happens. Depends on the intensity. If you're in a pond or in a sort of low density system, the changes are very slow or slower. If you're in a very intense system like a RAS, which is packed to the brim with fish at, let's say, 100 kilograms per cubic meter, the changes happen within minutes or just a few hours. Next slide. And basically in a RAS, when the machines are pretty much keeping your fish alive, you have to understand that the moment you lose the machines, you don't have a lot of time left. Because if you have been feeding, the dynamics on the pollution of the water cannot be stopped. And this slide is just a few examples of everything that can go wrong in a RAS that is full of fish. The most important is obviously oxygen, and oxygen means either dosing of oxygen or oxygen being brought into the fish by the water. So if you lose oxygen and or water flow, you will lose your fish very fast. If you lose your biofilters or mechanical filters or CO2 strippers, you do enter into problems, but they don't tend to be as acute and dramatic. It's something that is a problem that drags along the days, and you're spending your days trying to fix it, and you might lose some fish in the process. But it's not it doesn't tend to be catastrophic. But again, it's all about keeping the flows going, keeping the machines running, and knowing that, because feed drives everything. If you're feeding a lot, obviously you are at risk of something going wrong fast if you lose your machines. Next slide. Temperature, not much to say about it, except for the fact that in my experience, I have noted that tropical fish are far more sensitive to obviously water cooling down. Temperate fish from let's say temperate areas, like for example Europe, obviously because they are used to seasons, it's a lot more forgiving on how you can change temperatures. Obviously they all have an optimum. Economically, what works best is to have your fish obviously closer to the climate area where they belong, so you don't have to spend that much money in chilling or heating the water. But pretty much that's it. Something that is important, if you are outside of the ideal climate area, you need to be very diligent in how you dimension your heating and cooling systems, because often happens that those are not dimensioned properly, and then you start a farm and your fish are either warmer or colder than they should be, and basically you have to redo your cooling or heating plans all over again because of basically a bad calculation, and that tends to happen often. So when you need to dimension these things, look for good advice on how to design and engineer either heating plans or cooling plans. Next slide. Yeah, basically very easy to measure temperature, of course. Thermometers, probes can do that as well. You can go as cheap as you want or as expensive as you want. It's basically the simplest parameter to keep in control. Next slide. And to heat the water or cool the water, or no, to heat the system or cool the system, you can use machines, and that is something like a boiler or a resistance heater to heat the water up. You can use heat pumps. They are becoming more popular. Heat pumps work in the same principle as an air conditioner. You can use waste heat sources. In Europe, it's common that we use sources coming, for example, from a greenhouse or a power plant to heat a fish farm. And to cool them it's a lot more difficult, because to cool it you only have electricity and heat pumps and chillers to do that. But in some cases you may have a water source, cold water source, and that could allow you to cool down your system as well. Something that's important to note is, of course, if your animals are beyond their ideal range, then you have to act. Normally, if the water starts getting cooler, they will feed less and they will become a little less active. So you need to adapt your feeding schedule for that. If the water starts becoming warmer, the dissolved oxygen in the water will also go down, and you have to be more careful with how you're feeding, because there's less oxygen available in the water for the fish. But we will look into that later when we talk about oxygen. All right. And if you're talking about tilapia, just a little table for you in the next slide to check. You will be able to get these materials and use them for your own purposes. These are just the optimum temperature for tilapia. You can see that the range is quite small compared to a fish like a carp or a trout or a sea bass, with a very narrow optimum. Next slide. And then we look into oxygen. Of course, oxygen is the most essential parameter. Without oxygen, we're all dead. Both fish and bacteria in the system need it. And oxygen, you need to find ways to transport oxygen in the water when your systems are anything but let's say extensive or low density, and that can be done by different means. For now, obviously, what you need to understand is that 4 milligram per liter limit that you see in the graph should be about a minimum for most fishes. Catfish, of course, can gulp air, atmospheric air, and they can obviously survive in low oxygen conditions. But besides that, the vast majority of fish do not do well with lower oxygen than that concentrations than 4 milligrams per liter. That also there's a difference on just resistant warm water species like tilapia. Salmonids don't do well below 6 milligrams. And you don't want to keep marine species also in lower than 5 or 6. So just to keep in mind, those are sort of hard limits for aquaculture. Next slide. And because oxygen is so important, you don't have a lot of time to respond if oxygen goes down. So you have to continue to monitor it. And the more intensive the system becomes, the more often you have to monitor this. If in a low density system with not a lot of fish, you probably can do it once a day or even once every few days. Or you can do it with, for example, day and night cycles to try to plot how your oxygen goes through the hours in a day. But once you're talking about a RAS that is very intensive, this has to be done continuously, which means you need sensors that are connected to computers and are logging oxygen every second. And the moment something goes out of the ordinary, you get a phone call or some alarm in your room turns on and you need to take action. If you want to measure oxygen, we give you here a link to a website where you can input basically some values, for example, temperature, the measurement that you can get from a probe, and then you will get a saturation value. So what this means is that oxygen and all gases, by that matter, basically, the colder the water is, the more room there is for these gases to be dissolved in the water. And this is because the molecules the gas molecules in the water move a lot less when the water is colder. When the water is warmer, they move a lot more, and there's basically less room for them to be there, which means in warmer water, there's less oxygen available. And why is this important? This is important because I told you before, the 4 milligram per liter value for your fish is just a hard value, but you also must understand the percentage saturation of oxygen that is in the water for your system. Why? Because fish tend to have an ideal range in which oxygen can travel more or less freely into the gill without the fish doing too much effort. And that value is about 80-85% saturation of oxygen. So because the saturation of oxygen will depend on temperature, you need to know the temperature and you need to know the concentration. Another reason why saturation is important is because there's also an upper limit where we don't know exactly that limit, but there is an upper limit in which you probably shouldn't be oxygenating more. And that is, in landing, we tend to go for about 200 and 250% saturation of oxygen. What this means is that in a RAS, you're injecting pure oxygen from a pure oxygen source, like a bottle, a gas bottle or a cryogenic tank, and you can double or triple the amount of oxygen that is normally in the water at atmospheric pressure. That means you can hold a lot more fish, but there's also evidence that the fish don't really like when there's too much oxygen in the water. We don't kill them, but we see that they avoid areas with very high oxygen. So basically, you know now that you have an ideal range of 80-85%. You don't want to go below that, to about maybe 200-250% saturation. And you can use sensors to track that. And as I said before, you also have your lower limit of 4 to 6 milligrams per liter that you can also measure to keep your fish healthy. Next slide, please. And these are the things that you can use to measure oxygen very quickly. Aquarium kits can do that, and then you can use probes. Obviously, the peace of mind that comes with having online monitoring, it's worth every penny. So we always recommend using some sort of probe when you have your system running at high intensity. And when I say high intensity with tilapia, I would say above probably 40 to 60 kilograms per cube. You want to have probes in the system. Next slide. It goes without saying that you need the probes, but you can obviously, of course, look at your fish. And the first thing that you can look at is that your fish are not eating properly. Then you can see that if they are gasping for air at the surface, that's already bad. And then if that happens, the first thing you need to do is stop feeding straight away. And then you can start doing a few other things. You can aerate your tank if you can. In RAS, normally it might be that you're not getting enough water flow into your tank. So by you simply speeding up pumps or turning on more pumps, you can get that solved. You will also see more chronically that the cleaner your water is, the less oxygen consumption there is, because bacteria consume as much oxygen as your fish. So if you can plan to remove more solids, meaning more bacteria from the water, you will obviously reduce your oxygen consumption. And this has a huge effect. We will explore a little bit more when we talk about solids. And back to your table. Now we saw temperature. Now we have oxygen. This is your values, your reference values that you want to have. You can see there that the optimum for tilapia is 60 to 100. Yes, it's a minimum optimum, but ventilation rate, normally I prefer to keep it at about 80. But again, you will not kill your fish at 60. And Zala now goes with pH.
Okay, so one of the parameters that it's really connected to multiple others, it's a pH, right? So the pH level of water affects the chemical balance and availability of different nutrients in aquatic system. And what's just a bit of basic of the pH, we measure how acidic or alkaline on the scale from 1 to 14 is our water, where 7 is neutral. And as you can also see on the picture, also fish like to be somewhere around neutral, not too basic, not too acidic, right? There is also an important fact when we talk about the pH scale. It's not just linear scale, it's logarithmic scale. So the difference between 1 and 2, it's 10 times smaller than between 2 and 3. So when you drop the pH, be aware that you have this logarithmic difference. And when we talk about the aquaculture or aquaponics, most organisms prefer the pH somewhere around 6.5 to 8.5. And going out of those ranges, we can cause the stress to the system, reduce the efficiency. And one of those things that it's really important, it's biofiltration. So also our bacteria do not like to go out of this range. Just on the side note, simplified, the pH alone, it's not the one that would kill the fish, but it's other parameters that are affected by the pH that will manage to do that much faster than a pH on its own. So how do we monitor the pH, right? So as mentioned, there are some events and processes that can affect the pH levels and can quickly change the pH of your systems. It goes from the nitrification, fish stock densities, especially if they are too high, and plankton contamination caused by photosynthesis. So the simplest way how to measure the pH is with the pH test strips, which are the cheapest methods, but not so precise method. Then the second option are the water test kits that are a bit more expensive, but are colorimetric tests. And then one of the more expensive ones, it's using the probes, but it results in the value. Or the same as we said for oxygen, you can also keep the values online and use the online monitoring tool connected to the pH probes. However, there are a few things that we really have to be careful about, right? So when we talk about the tests, don't forget also on the expiration dates, right? So every time you're talking about the tests, check if the tests are expired, because this can result in the wrong values and you can kill your fish, right? Same goes for the probes. Do not forget to calibrate them, right? And trust yourself while you do that, because if you observe the fish and fish are swimming fine and your probe is saying that the pH is 14, do not just add acids just because the pH probe said it's 14. First, make sure that you're sure the results are correct. Maybe check it with another test, check with the calibration solution, and then react. But first, really observe the fish, right? So when we talk about the pH, because it's extremely important parameter, please make sure that when you measure it and cross-verify your results with other tests, right? And also regularly calibrate the sensors. So what to do if we have low pH in the system? One, in aquaculture, one of the most used ones, it's sodium bicarbonate, because it also gives you a buffer capacity. We will talk about later with alkalinity. You can also use the stronger bases, for example, calcium hydroxide or potassium hydroxide. However, please be slow, go slow. Do not just drop everything into the fish tank, but calculate your values, give these values to somebody else to recheck it if this is really what you have to add. Mix it well, so dilute it first already in lower concentrations and then add it step by step and observe your fish. Maybe add few milliliters, not more. Observe your fish, and if possible, you add it after the tank. So not that you drop everything just before the tank, before the fish, but you drop it slowly after the tank, that the system has time to react. Also with this, you do not kill or biofilter or the fish. So step by step. Same goes for the high pH. Normally, this is not a problem with the long-running systems, but can be a problem if you started the system on new, meaning that you have still high pH of the fresh water. For this, you could also use some acids, for example, phosphoric acid or nitric acid. But normally in running system, you will face more low pH than the higher pH concentrations. Really important to do not just add something to the system that you do not kill your fish. And the same as we said before, the pH somewhere around 6.5, 7.8. So we keep it in the range that it's good for the fish and it's also good for bacteria. Of course, the tolerance level is a bit higher. However, if possible, keep it in the optimum level. So now we come to the nitrogen. And for this, I wanted to share a short video with you that my coworker prepared. We will share also the link of the video with you, because I will just show you the first section. And also if you would like to recap or see it in the better quality.
Have you ever seen this thing? Actually, it is just a piece of plastic called a biocarrier. It holds the potential to host millions of nitrifying bacteria on its very high surface area. They exist in all different materials and forms with the similarity that the autotrophic bacteria can live on them. And they are the key component for the nitrification process in a biofilter. But why is a biofilter necessary in a recirculating aquaculture and aquaponics system? Fish excrete ammonia mainly through their gills and urine. It accumulates in a short amount of time and can be fatal to the fish if not properly managed. In contact with water, ammonia exists in two forms: ammonia, NH3, and charged ammonium, NH4+. Ammonia is very toxic for the fish, while ammonium is less harmful. The balance between these forms is determined by the pH of the water. At a low pH, so acidic water, the equilibrium is shifted towards ammonium, the less toxic form. At a high pH, however, more ammonia is present and therefore increasing the toxicity of the compound. Thus, it is important to monitor the pH to avoid a fatal increase of the highly toxic ammonia. Furthermore, these two compounds need to be continuously removed in order to have a functioning system. And this is why we need a biofilter. In the biofilter, we cultivate helpful bacteria. They convert the highly toxic ammonia in the water into less toxic nitrites, so NO2-, and then into far less harmful nitrates, NO3-. The product, so the nitrate, is relatively harmless to the fish and is a valuable nutrient for plants in an aquaponic system. However,
Okay, so hopefully you enjoyed the video, and now we go a bit back to theory, right? So as Natalie already mentioned in the video, nitrogen is one of the crucial nutrients for when we talk about the fish, or also about the plants, and of course bacteria. When we are talking about nitrogen, we are talking about ammonia and ammonium. So total ammonia nitrogen is the total amount of nitrogen in form of both forms, right? So we talk about ammonia and ammonium in the water. And when you buy the kits, normally, even though it's written the test for ammonia or ammonium, what you measure, it's actually both. So you measure ton. Just be aware of that. And in fully functional unit, we have with adequate biofilter, ton and NO2 levels should be close to 0, or at most in the range of 0.25 to 1 milligram per liter. Definitely not higher, because otherwise you will kill your fish, especially if your pH is too high. But we come to this later. So in the first step of nitrification, TAN, it's transformed into highly toxic NO2, right? This one is even more dangerous than ammonium. After that, NO2 is converted into less toxic NO3, as Natalie already mentioned in the video. And for this, we need bacteria and a lot of oxygen. So that's why monitoring our oxygen levels is really, really important. And sometimes bacteria, especially when we have the system with the catfish, they need even more oxygen than catfish itself. So it's really important that you keep the biofilter going. But because we do not complicate enough, right? Nitrogen gets even a bit more complicated, right? In literature, you can find different values or how those concentrations are written. So the most important part is that you understand that you can report the values in two different ways. Or you report the values in form of amount of nitrogen in the form of ammonia, which is this one. So we have NH3N. So here we are talking only about the nitrogen in that form, or it's reported in form of NH3, which is actually the whole molecule. But because the hydrogen is quite light, it has low molecular mass, there is not much difference. But when we are talking about NO2 or NO3, because it's bound with oxygen, these values vary a lot. So if you're reporting the amount of nitrogen in form of NO2 or NO2N, it makes a difference of the factor almost 3.3. So here you have to be careful when you report the values. Or when you read it, what you got, that you know that you do not kill your fish if you report one and the parameters are written in the second one. And when we talk about the bacteria and the nitrification process, also bacteria are growing a bit differently. So we have different bacteria in the system. And when we start our system, some bacteria are growing slower, some are growing a bit faster. And normally the bacteria that are transforming ammonia to NO2 grow a bit faster compared to bacteria that are transferring NO2 to NO3. So if you're monitoring only ammonia and NO3 levels, so the red and the green line, and you say like, hey, now my ammonia went down, now I can put fish in my system, it might happen that this orange peak of NO2, it's still coming. So you would actually kill your fish because the second peak of the most important and more dangerous nitrogen form is still coming, right? And here, the pH has really, really important function, right? So when we talk about ammonium and ammonia correlation, it really depends on the pH. So everything green, it's my good zone, right? And then we have the yellow one, which is, okay, fish are still fine, but the red part, it's really bad. Do not put fish in those ranges, right? And that you do not always have to check how the ammonia and ammonium are changing on the pH. There is online calculator where you can enter your values of what you measured with your TAN test kit, what is your salinity if you have it, and then also, of course, the pH, which will then result in the values to know if your fish are fine or you should react. But first we go how to measure it. So when we talk about the monitoring, you have different options. Cheaper ones, of course, are not as precise. However, there are some that are much more expensive, but then you're sure that the values are correct. So depending how well you know your system, depending how much money you have available, you can then adapt the methods that you would like to use. One of the cheapest methods are the test strips, which they give you just approximation of what's inside, but you have to monitor it regularly so you get the trend. Then we have the colorimetric water test kits. So normally they come for the aquaria in those boxes. Or then we have the spectrophotometric tests that you normally have to buy, and this is more laboratory use. You can also send your samples to specific laboratories, and normally they will analyze your samples with ion chromatography, where you will then get the values for ammonia, NO2, and NO3. Or if you have really big systems and big budgets, one option is also that you use the online sensors that will monitor your amounts constantly. So what to do if these values are out of the range, right? So when we talk about high ammonium levels, we should really increase the biofiltration if this is possible, reduce the feeding, partially do the water exchange. However, always make sure on the pH, do not forget on the pH, and improve the aeration. When we talk about the high NO2 levels, it's again, check your biofiltration. Add oxygen, maybe the biofilter does not have enough oxygen, maybe there are some anaerobic zones somewhere. To prevent that NO2 would damage your fish, you can in aquaculture add the salt into your system. If this happens in your aquaponics system, if you have an option, the best would be that you would decouple the system in that time, run the aquaculture with the salt to keep your fish healthy. And once this is solved, you can combine these systems back together. And of course, partial water exchange, but please keep track on the levels for the pH. And when we talk about the NO3 levels, there are different options. One option is the water exchange, or if you run the aquaponics system, add more plants, because the plants like NO3, so they will take it up and serve as they will just eat it up, so you don't have to worry about it anymore. Like we said, there are different options, so be careful how it's written, because in our lab, we always report all the values in those forms, meaning how much nitrogen is present in specific forms. So how much nitrogen is present in the form of NO2, for example. Those are our values. How we do it in our system, you can adapt those values depending on your fish, and also how your fish react to specific parameters. It also depends on different fish species or even different variety. Carlos, now back to you with alkalinity.
Yes, thanks. All right. First, apologies for the huge blocks of text in the slides. We thought it would be nice to keep those, because then you can read on them and use them as study material. All right. And then for alkalinity, we include alkalinity because there tends to be a lot of confusion between what pH, alkalinity, and hardness, are in the system and how they interact. The disclaimer here is that normally in the aquarium industry, they talk a lot about hardness, carbon hardness, and so on. In RAS, we sort of avoid or forget about all of that, and we just simply talk about alkalinity expressed as a milligram per liter of calcium carbonate. That works enough, good enough for us. And what is alkalinity? Basically, they describe it as the buffering capacity of a system, or the capacity of the system to resist to changes in pH. That means that if you have a water with absolutely no alkalinity in it, and you add an acid or a base, the pH in the water will swing quicker. And if that same water you add a source of alkalinity and you try to do the same pH change with an acid or a base, that movement of pH will not happen as fast as an unbuffered water. Basically, what a carbonate alkalinity source does to the water is that if you add an acid to the water, basically the acid will start to dissolve first your alkalinity in the water before it starts acidifying the water. That's pretty much the gist of it, and that is one reason why you want to have alkalinity in the water. But the other reason, or the most important reason, is that if you're using a biofilter, the nitrifying bacteria use alkalinity as a food source. If you don't have alkalinity in the water, your bacteria are basically starving and they cannot do their job. So you need to have alkalinity for them. Something that it's important to note is that in the carbonate system, in a RAS, alkalinity doesn't change with the CO2 pH dynamic. It could change in the long term as the system tries to find an equilibrium, but in your day-to-day activity in a farm or in a system with a RAS, it just doesn't. Your alkalinity will just gradually drop as you feed your system, you add feed to the system, and the pH and CO2 dynamic will happen a lot quicker in terms of hours. But I will explain more about CO2 later. But for now, just understand that alkalinity is a big, slow-moving truck in your system that is relatively easy to control, and you need to control it simply by adding. The easiest is to add bicarbonate in your system. There are other bases, but bicarbonate is relatively mild and safe to use, so you can use that. And you use it at a reason of about 250 grams of bicarbonate per kilogram of feed that you supply to the system. You measure it mostly with colorimetric tests or laboratory kits. To be honest, the colorimetric tests, they just do the job. They normally give you sort of German degrees, which is basically for every drop that you add into your little beaker, the color in the water starts changing, and then you know that after certain drops, the water changes color, and that is the reading that you want. In practice, you need for a RAS something between, these typical JBL tests, you want 6 to 7 drops changing that color, and when that happens, if you do the math, you will find an alkalinity level that is the correct one. And what is the correct one? The correct one is if you see this table in the slide 32, 31 in the slide itself. If you look at that table, you want your water to be moderately hard. You want the water to have at least 70 milligrams per liter of alkalinity, and ideally more than 100. That is a level that the biofilters like to have. So what happens if you have low alkalinity? The only thing you need to do is add more sources of alkalinity. I gave you a rule of thumb in terms of per kilogram of feed, that is 250 grams of bicarbonate per kilogram of feed. Here you have another one that is quite useful as well. If you want to lift alkalinity by 10 milligrams per liter, you need to add 13 grams of bicarbonate per cubic meter. So you can control it however you want. You can control it based on your system volume, or you can control it based on your feed load. Both will work. Is alkalinity not a problem? It's not. There's really, you can go as high as you want in super alkaline waters. What you get is like incrustations in pipes and hardware and stuff like that. It's not the end of the day. But there are two things that you have to be careful about. One is that bases may or may not have an effect on carbonate alkalinity. For example, bicarbonate, because it has carbonate, will add alkalinity and will increase pH in the system because it's a base. But if for example, use something like sodium hydroxide, that is a very strong base. It's really good for increasing your pH, but has no alkalinity in it. At least not carbonate alkalinity, which is what you need. So bear in mind that the sources of carbonates or alkalinity that you're using, they may be strong or weak bases. And for every, let's say, gram of alkalinity that you want to replenish in your system, you might be increasing pH more than what you expected. So be careful with that. Normally, again, bicarbonate tends to be the super simple way of going about this. Also, calcium carbonate works as well in systems without plants. If you have plants, then you have to use more of a potassium based base. Also, in systems with plants, sodium is not good for them. So you have to avoid the sodium bicarbonate one and use base alkalinity sources that don't have sodium in them. The change in alkalinity, again, is very gradual, and it happens when you feed, because the biofilter, the nitrification process, is an acid-forming process. There's nitric acid in there when the bacteria are converting ammonia to nitrate. And that nitric acid is what basically eats your alkalinity. That's why you need to replenish it. So it's something that you do daily. You might automate it. For example, you can have a feed hopper doing that, or you can have a bucket with dissolved alkalinity buffer and then basically a dosing pump, or you can simply throw a bucket of the stuff in a well-mixed area of your system, and that's about it. And the next slide, here's your briefing table. What is good alkalinity? I would recommend for biofilters to be close to 100. And you can see that, yeah, the fish have a huge range of tolerance, but it's more important for the biofilter than for the fish. So keep in mind that this is mostly for the biofilter. Let's go into CO2. For the most part, CO2 will not be a problem for you guys, for anyone doing ponds and extensive or semi-intensive systems. CO2 only starts becoming a problem when you start adding pure oxygen to the water. So for most of the cases that you may be encountering, this will not be an issue. However, I wanted to include this because the industry is going into a more technified, we're technifying more and intensifying more. So eventually you're going to come across having to add pure oxygen in your systems. I think it's just only a matter of time. And the other reason is there's a lot of confusion, or there tends to be a lot of confusion about the CO2 and the pH dynamics in systems. So might as well, guys, give you a bit of an introduction, so at least you're aware for when you encounter this in the future, doesn't take you by surprise. So of course, fish, bacteria, and ourselves, we breathe in oxygen, we expel CO2. When that happens in water, CO2 is converted to carbonic acid, and that lowers the pH of the water. And that is an effect you can see very, very fast in an intensive RAS. If you have a fish tank, you start feeding and you put a pH probe and a CO2 probe, or either, and you start feeding, you will see that drop happen in basically minutes. You will see a drop in pH in the tank simply because CO2 is being produced by the fish as they are, very excited eating and what have you. Keep in mind that the bacteria will do this as well. If your system has a regular solids removal step, like a settling basin or a drum filter with big meshes, there's going to be a lot of bacteria in the water, and they can consume as much oxygen and produce as much CO2 as your fish. So keep that in mind. Tilapia and catfish are very resistant to CO2. They can take concentrations that would basically kill other fish, but they also have a limit. But what you will normally see is that you don't kill them, but they just stop eating and they become very lethargic. And because people normally are not aware of CO2 being a problem, they might feel that something else is wrong, and it's just a matter of CO2 being a problem. It's not written here, but there's another consequence of CO2, especially in enclosed spaces, like an indoor farm, which is on your safety. If there's a lot of CO2 in the water and you have a sort of a cascade or a part of the system that is in contact with the air, that CO2 is going on in your room and you're breathing that, and you can start feeling dizzy, and well, it's simply not safe for you to be in that type of room if it's not properly ventilated. Obviously, what you need to understand is that if CO2 is high, your pH will go down, and if CO2 is low, your pH will go up. If your pH goes up, then you might enter into ammonia toxicity issues, remember? So you also need to be aware of the consequences of CO2, of stripping too much CO2 from the water if you don't have a fully functioning biofilter. And for us, high CO2, low CO2 and high pH, tends to be typical of systems that are just getting started, where we have a lot of aeration and a lot of machines basically stripping CO2 in preparation for when the system is full of fish, but there's no fish yet. So whatever little bit of CO2 that is in the water is being extracted, and then the pH is too high. Normally, in this startup phase, what we try to do is be very careful of the biofilter, but as soon as the animals start growing and feeding more and more and more, that pH starts dropping down nicely as your CO2 increases just a little bit. So it tends to be the high CO2 tends to be a problem of too much fish, not enough filtration, and the very low CO2, the dangerously low CO2, tends to be a problem of excess stripping capacity when we don't have enough fish biomass in the water. And how do you measure it? The first recommendation from me is to have a CO2 probe. They are very expensive. They cost something like 1,000 euros each. They can be both standalone or can be connected to a computer, but the accuracy and the reliability, the accuracy and the capacity, of course, of connecting them to other alarm systems or or for example, pH regulation systems. That is fantastic. You can also use tests, but again, in very intensive systems, because the CO2 swings so fast, you need more of online monitoring. There is a CO2 level calculator you can use. Linda will probably give you the link in the chat. Keep in mind, this only works for fresh water. This type of calculators. In seawater, the calculators are a lot less reliable. And when I say fresh water, normally it's about 1 to 2 milligrams grams per liter of salinity. Beyond that, these calculators don't work as well. How do we control CO2? How do we strip it? Basically, how do we take it out of the water? Anything that creates either splashes of water between, basically contact air to water will strip some of the CO2. For example, you can put air stones. This is very, very simple to do. You can put them about 0.5 meter on the water column to not basically put so much effort on your air pumps or blowers, and heavy diffusion at about, if you have a tank and the tank is flowing at about 1 cubic meter an hour, if you put 5 cubic meters an hour of air in that tank, you will strip a lot of the CO2. So about gas to liquid ratio of 1 to 5. That works very well. What works even better is a packed column, which is basically a tank with a shower of water on the top, and the water is trickling down in the form of a shower, and we have a fan basically blowing or sucking air through that shower of water, and that goes outside of the building. That sort of counter-current contact of air with water is very efficient for stripping CO2, and ventilates your room as well. So you can see a picture there of this sort of square block that we have there. It's basically a degasser with water entering at the top, and you can see at the top of the picture there's a fan there extracting air out. If you look at the diagram on the slide, is that exact representation of what we did obviously in a process form. There's a lot of CO2 extracted from this stuff. In that particular one, I once made the mistake of putting my face next to where the exhaust from the vent, so from the fan was on the outside of the room, and I almost fainted. It's a lot of CO2 that these things extract. In the next slide, you will see a very quick chart for you to take action. I created this one, part of the manuals that we deliver in Landing for systems. Very, very, very simple. You can measure your alkalinity, you can measure your pH, and based on the results, here you have actions that you can take. You can stop adding your alkalinity buffer, you can start adding your alkalinity buffer, or you can stop or increase your CO2 removal based on the values that you get here. So you can see that the optimal there, you want between, let's say, between 1 and almost 300 milligrams per liter on alkalinity, and you want your pH between 7 and 8. Between that, you should be fine. If you ever encounter CO2 levels that are too high, maybe in your own farm, or because you're consulting for someone and you visited some farm and you can see that there's a problem, there's some of the things you can do. Of course, increasing aeration, it helps a lot, literally just to grab a blower or some air pumps and some diffusers and chuck them in some part of the system and aerate a lot. Remember to ventilate the room, because that CO2 is going into the room if it's a closed space. You can increase water exchanges, because the water that is going to be coming into your farm hopefully doesn't have as much CO2 or has no CO2. So if you're dumping some of that CO2 in the system and obviously replenishing some clean water without CO2. You can, of course, as I said, stop feeding, stop the loading. That will immediately decrease CO2 production by fish and bacteria. And something that can also be done is that simply you can increase the pH of the water, because remember, if the pH goes up, CO2 goes down. As long as your biofilter is working and as long as you're careful, you can do that. And in fact, in very intense RAS with fish species that are very sensitive to CO2, mostly marine ones, they are doing this these days. They have little dosing pumps that are literally dosing hydroxide, sodium hydroxide, or a very strong base into the tank itself to try to bring the pH up and the CO2 down in moments where the fish are too excited. So if you do that carefully, or you do it in an automatic way, that's a way of doing it. The drawback is that those bases are very expensive chemicals, so you don't want to do that all the time. In the long term, if you always have CO2 levels that are higher, that means that your system was not dimensioned properly to remove CO2. So you need to either accept your reality and know that you will be simply producing less because your system cannot take the loading, or you're going to have to upgrade your system, and that includes improving your solids removal processes so your bacteria consume less oxygen and produce less CO2. You can add plants or seaweeds or so on that allow you to take some of that CO2, very experimental, or you can, that you have to improve your CO2 removal processes. And this is it for tilapia on CO2. You want to have as low as possible, of course, but they can take a lot. They can take up to close to 40. Remember something on catfish. Catfish gulp air from the atmosphere, but then when they exhale in the water. So you say, oh, I don't have any problems, but then you may be having CO2 accumulation problems in your catfish farm because there's no way to remove it. So keep in mind, in very intensive catfish farming systems, you need a CO2 stripping step. Besides the fact that Zala said that you need to keep the oxygen levels high for your bacteria, even though the fish don't care about it that much. And then let's go a little bit into salinity. Not going to go too much into that because, of course, we're talking about fresh water, and of course, it's harmful for plants. But Zala mentioned it before, talking about NO2, nitrite. And I wanted to expand a little bit on that. Just as a refresher. Salinity, yes, it's bad for plants, but it's good for fish. Basically, fish have an internal salinity. And if the salinity in the water is closer to their internal salinity, then the fish don't have to osmoregulate as much, which means they grow more efficiently. They spend less energy in osmoregulation. How much can you afford it? Of course. Salt is expensive if you don't have access to a good source of seawater and so on. The complications might be more than just having a fish happy on the right osmotic environment. But you can use it to reduce osmotic stress, especially when the fish are sick. You can use also an increase in salinity to reduce nitrite or NO2 toxicity. It helps a lot. So keep in mind that if you ever run into this type of problems, you know that you can use salt. It also, of course, is used to combat sometimes some parasites or some disorders. To me, the part that I like the most about this particular topic is that the chloride ions in salt water or in a saline solution that has obviously different type of ions, but including chloride, is that the chloride basically blocks in a membrane. It blocks the NO2 and NO3 from going into the membrane. And the cool thing is that it doesn't matter what type of membrane. It can be the membrane of a gill, it can be the membrane of a plant, and it can be an artificial membrane like a nanofiltration membrane. It's the same the same physical phenomenon is occurring at all of those membranes, across all of these membranes. This is a super cool thing to understand. So, and this is why you use chloride, and this is why you want to avoid chloride, depending on the case. All right, and the last thing about salinity, if you can do a brackish system, to me that's perfect. The fish are really happy. The system works very well. But above this salinity that I'm giving you there, about 12 to 15 milligrams per liter, there's going to be a bacterial succession happening where marine organisms are taking over the freshwater organisms. So you will see your biofilter basically crashing for a while and then adapting to the new salinity. In our experience, as long as you stay in brackish up until this level, you should be fine. If you go higher, then you transition into a marine system, and the whole system changes. On the next slide, TSS, suspended solids. Doesn't matter that much in tilapia and catfish, but it's important that we understand why it matters in general, because it can make our lives easier or it can make our life a headache. Of course, solids in aquaculture systems are feces, feed that the fish didn't eat, bacterial flocks, bacterial biofilms that are falling off and basically getting suspended in the water. All of that stuff. TSS can be a good thing, or it can be a very bad thing. It is a good thing in systems where the animals like dark water. They feel calmer in darker water. Shrimps like it, tilapia don't mind it, etc. It can be a good thing in bioflux systems, because it is the suspended solids what acts as a substrate for bacteria to attach and do their work in the water. So you want high TSS in a bioflux system. But it's pretty much bad for any other type of system, because you will have a lot of bacteria consuming your oxygen, which is expensive, and producing CO2. And you cannot see the animals. You will get solids accumulating in pipes and so on, and make your maintenance a bit of a nightmare. So, it really depends on on what type of system you're aiming for. If you want a clean, indoor, intensive RAS, you want TSS out as much as possible. If you have ponds or you have a bioflux system, it's not that important. But okay, the distinction between how you measure things. Suspended solids, of course, you're looking at a particulate matter and the solids themselves in the water, and turbidity is simply a measure of how the light is scattered and blocked in the water. Two ways of measuring things. In the end, it all indicates if you just have some sort of solids or bacterial accumulation in the system. Basically, in the next slide, I already explained, I went a bit too far, but basically, if you have more solids, you have more food for bacteria. If you have too much solids, you can have gills getting clogged. But again, this is very extreme levels, and the solids start being big and then break down more and more and more to a moment where it's almost impossible to take them out. So if your goal was to take out solids, you know that you have to take them out before they break down. And in intensive RAS, the accumulation itself is not that much of a problem, because you will find filters where you keep your levels down. But what we have seen in RAS is that if you have an overload of solids and you're not taking them out, there's a lot of bacteria that will go into those solids, eat them, and the bacteria will bloom in your system. When the bacteria bloom in your system, normally the ones that grow the fastest tend to be opportunistic, and some of them tend to be the pathogenic ones. So what we normally see is that these blooms of bacteria are normally followed by some fish getting sick with systemic bacterial infections, because among this huge bloom of bacteria, some of them are pathogenic, and some of them may find the opportunity to jump basically into your fish. So when you're dealing with solids in an intensive system, again, the limits will be kept by the filters, but you don't want very big swings in your organic load in the system, right? So be careful with how fast you feed, because or be careful if you lose a mechanical filter and you're not filtering solids out, stop feeding as much as possible and try to control your bacterial load. How do you remove the solids in the next slide? Well, we call it mechanical filters, but you probably know in the literature or on the internet, you can find anything from a swimming pool sand filter to drum filters that are the size of a school bus. You can do it by gravity settling. You can simply flush water, dirty water with clean water, and so on. And how do you get rid of turbidity? You normally need something that kills bacteria, like UV, and you need some sort of an oxidizer. And ozone treatment tends to be the most popular oxidizer, but there are many, including, for example, adding bleach to the water in small amounts has been traditionally an oxidizing process that helps keeping that turbidity and those microbial communities in check. All right. Then one of the last slides, we're going to talk about a little bit about water sources. You will find in your career in aquaculture that good water sources are becoming rarer and rarer. It's really difficult to find these days sites with really good water source. With climate change, it's going to get worse. So we have to be very mindful of that. The best site you can ever find is a site with all the water that you need and clean water. If you have that, you have struck gold, and your life will be a lot easier than in many other cases. Again, this is becoming a rare occurrence, at least in Europe. But then, if not, anyway, you're going to have to run your water analysis in any sources, and ideally through time, so you can see if there's an evolution in how the water quality parameters are changing. And your typical sources are going to be either tap water, which may have some chlorine or residual chlorine from obviously the treatment systems that are upstream of your source, and they cost a ton of money. Municipal water is for homes, small flows. It's never, it's rarely for a large farm. You will often find the most common is surface water. That can be rivers, ponds, lakes, the ocean, of course. The good thing about this is that it's more abundant, of course, relatively easy to find. In some cases, the farms are becoming so large that this is the only source we can use. But of course, surface waters will come with microbes or may come contaminated. And you will have variability with temperatures, if there's rainy seasons, etc. Of course, or if there's activities, obviously, in your watershed that may affect that water source. You have to be aware of that. This is a critical problem in places like Southeast Asia, for example, in Vietnam, where everybody uses surface waters. Everyone is basically next to each other, and you can see the outfalls of some farms are used as the intakes of another farm, and that's obviously a biosecurity nightmare. But that's where we are. If you can use groundwater or borehole water, often is a great source of water because it's microbially stable. It doesn't have microbes, but it may come with some contamination, or it may come with some dissolved gases in the water. So you need to be aware of those, so you can have a treatment system based on what you find. If you find groundwater with bacterial activity, that means that groundwater has probably been contaminated by often a local or a localized activity. For example, you may have water treatment plants or a sewage system of a city that is leaking into the ground and is contaminating sources of groundwater. So these are things that you have to be aware of. And the last one, in very rainy areas, you can get rainwater. The problem is that it's almost like distilled water. It has no alkalinity, no ions, so you need to add alkalinity sources to that water. In our experience, we used rainwater once in a system close to The Hague, that is in the north of the Netherlands. Very urbanized area, had problems of acid rain in the past, and we used rainwater there, and we killed fish. So the rainwater was not the clean source that we were expecting. So be mindful of that, because also rain, as it falls from the sky, falls into structures like buildings and roads and so on, and then trickles into a place where you collect it. In that process, it might be dragging in all sorts of pollutants. So be very careful with rainwater, especially close to urban areas, in my experience. And that's it for me.
Thank you very much. And now we come to the last part. That's the homework for the ones that would like to have the ELISA certificate. The same as always, I prepared you the Excel where you can fill in few things. So this week, what we would like from you, it's, since you heard a lot about the water parameters and so on, I prepared a daily timeline where you can enter the values. So I would like to know, how often would you like to measure different parameters in your farm? So what I emptied and left empty is the part about the water quality. So this is the part that I would like to hear from you. Which parameters you would like to measure when, how often. So here, for example, the schedule is prepared for 1 week. This is how we do it in our farm to make it easier for us, that on the upper part of our template, it's written on which days we would like to measure something, or on which day somebody has to check specific parameter, because not all parameters have to be checked daily. So what we do, it's on specific day we mark. So for example, on Monday, you have to check water temperature. On Wednesday, you have to check also the pH and ammonium, because the system is still quite new. You have to do it twice a week. Or maybe because my system is running for a longer period of time, I just do it once a week. So what I would like from you is that you fill in the water parameters and write me which parameters you would like to measure. So you get the same Excel. And then on the second part, it's now that you know how often you would like to measure it, I would like to know with what. What's available in your country, with what you would like to measure. Can you get it? What kind of test kits? And how much does it cost? Because one thing that it's really important is that before you start planning the farm, is that you are also aware of the costs that will occur when you are building it, and also later on for your business plan. So just that you get the estimation, what is possible, and just make me a list. And I will send you the Excel with my email that always comes after the webinar. So as conclusions, I also prepared the table with our approximation, how we suggest that you would do it, but I will send it to you after the people that are doing the homework will do the homework, so you will get it with the email next week. And there are some parameters that can be measured daily, some of them weekly, and some of them are just good to have, and especially if you cannot afford it. And in general, like we are repeating over every webinar, record keeping, educated staff, knowledge transfer are the key factors to keep your fish alive and to make a good business case. So with this, I would like to thank you, and we can move to the questions.
Yeah, I see a couple of questions from Ernest. I was answering them in the chat, but now I can answer them here. The first question that we were chatting about adding sugars in the water to promote bacterial growth. He asked me if adding sugar could make easier the start of a biofilter. The short answer is no, because you're simply promoting the wrong type of bacteria. Let me explain. In a biofilter, as you saw in the video, you have obviously the little carriers, the little plastic media that eventually get populated by bacteria. That is a process that is going to happen sooner or later, depending on how you mature the filter. You can speed up the process by adding nitrifying cultures that you can buy from companies that create them. You should shut down your UVs and all of your disinfection and basically bacteria killing processes when you're maturing a biofilter. But if you add sugar, what you're doing is you're creating a bloom of heterotrophs. And not really promoting the bacteria that you want, the nitrifiers. So why is it useful? Where is sugar adding useful? Is useful in a bioflux system, because in a bioflux system you don't have the plastic carriers. In a bioflux system, is the solids in the water, the flux themselves, act as carriers. So you can add sugar in a bioflux system to create that bloom of bacteria, increase your suspended solids to, let's say, about 400 milligrams per liter. And then there's so many solids in the water that then you can stop adding sugar and allow the nitrifiers to populate those little grains that are all floating in the water. And then you start having a bioflux that turns ammonia into nitrate. In that case, it works. In the other case, it can work, is that you can, if you have an emergency, you can add sugar to a RAS, but you would just create a very fast bloom. And in that bloom creation, the bacteria are taking nitrogen or ammonia from the water and turning it into biomass. So that's a way to sort of soak up ammonia very fast. And that works in the moment you do it, but then of course you end up with a system that is full of bacteria and full of solids, right? So you run into the next problem. You see how you control that bloom. And then that was the first answer to that first question. And then Ernest also asked, what type of carbohydrates can be used for a denitrifier? Pretty much anything. You can go vodka, sugar, molasses, ethanol, methanol, whatever. The more important thing here is that each carbon source promotes a different type of bacterial community, which means your denitrifying filter will behave differently based on what carbon source you use. What do people normally tend to use, or what traditionally people tend to use in RAS is methanol or ethanol. What the latest research that we have been doing suggests, especially with sludge reactors, suggests that the best carbon source to use is acetic acid, vinegar, basically. It's relatively cheap, it's safe, and it's very close to what the bacteria produce when they are fermenting sludge in a RAS. So basically you're promoting bacteria that are already there and they like to do their job in RAS. So I personally would go with acetic acid for a denitrification reactor in aquaculture. There's another question. It says we do replicate of the measurements. I don't understand the question too well. You, Zala?
Yeah, I think maybe you meant with if we do some measurements with the test kits, if you do multiple replication of each sample, it really depends how much you trust your measurements and how well you know your system. I would say when you start with the measurements, it's always good to do maybe a few more to get an idea how precise are the measurements, how do the tests work. But once you have a stable system, if you trust the device or if you trust the test kit that you're using, normally this is not necessary. But I would say if you get a strange value, this is definitely a case that you say, maybe I should repeat the test and check with something else. If this
calibrate. Always calibrate. Does denitrification remove phosphates or just nitrates? It's mostly removing nitrates, but there is some research being done. There's been research done that demonstrate that some phosphates is also being removed by especially sludge-based reactors. There is some phosphate removal going on also there. So yeah, they can, but the ones that use sludge. I don't know about the denitrification reactor basically based on carriers alone. Yeah, that's what I can tell you.
A question that came up repeatedly, guys, was the issue of the biocarriers being from plastic. So then we have a question for the lifespan of those plastic carriers. Maybe if there is some abrasive behavior that we have, microplastics in the system, and then also potential cleaning of those biocarriers. Could you elaborate on that?
Yes. We didn't know much about it, but there's some recent research being done by NTNU in Norway and with Joao and Nuno from Ciencia. They had a project doing this, where they were sampling for microplastics in a recirculation system, one made by ours with all the moving bed stuff and all the plastics going around, and they didn't find any. The only microplastics that they found were from fibers from the clothing of the staff. So those sort of the HTP, so high density polyethylene and polypropylene, all these plastics that we use for building these systems tend to be, we have evidence now they appear to be resistant to abrasion enough that those microplastics are not being produced in the system. So that's as far as we know from the last project that I've been involved with on that.
And maybe to add to that, since our systems are running quite some time, right? I was using the same biochips for the last 10 years, and the biochips still look completely new. So even if you grab them, you see that there is not many scratches, that mostly they have mechanical damage from us moving the biochips and not biochips actually moving in the system itself.
Yeah, and a general advice is if you have a working biofilter, just don't touch it. Don't clean it. Don't do anything. The older the biofilter is, the better it works. So treat them very, very carefully. They're asking us about phosphorus. Do you want to say anything about phosphorus, Zala?
I mean, depending for what, when we talk about phosphorus, at least in Europe, the new regulation is coming that they would like to reduce the amount of phosphates coming from the water. So a lot of people are doing research at the moment how to avoid them or reduce them in the outflow water. The research is still quite new. When it comes to the plants are happy. So if you use the aquaponic system, is good. Well, if you work with the aquaculture, there are already some ways how to remove it. But we are still quite at the beginning with that, I would say.
Yes. Phosphorus is, we haven't found a level where it becomes toxic to the fish. So for the recirculating water, it's a non-issue. It's more of a, as Zala says, more of a water treatment issue. Do we need to treat those? There's of course biological and chemical processes to try to remove phosphorus from water. As Zala says, we're working on that. Even in Landing, we're doing a bit of research work trying to come up with solutions. But the toxicity is actually the opposite. There's researchers in Wageningen University that are toying with the idea of increasing the phosphorus content in the water so high that actually the fish uptake it through the gills, so you don't have to supplement it with feeds. That's a very interesting idea that I would love to see being developed in the future. But that also tells me that it seems to be that, yeah, toxicity is not a problem. Then can we combine MBRs with RAS? Yes. The problem is that MBRs are very expensive. And compared to the typical filtration systems that we use, they treat very tiny flows of water. So your membrane installation would be enormous just to be viable, and that's really expensive. Something that you can check from the Freshwater Institute in the United States. They recently published some work on grabbing the sludge from drum filters and putting them in a denitrifying membrane bioreactor so they can remove nitrates there and then pump the water back, clean water back into the RAS. And that seems to be working very well. Of course, they do it on a lab scale, pilot scale. So would that also translate into a commercial plant? I'm still not too sure. Some remains to be seen.
So maybe one last question, because we are already at 10:30.
Carlos, do you go with this one, with the last one?
But aluminum sulfate?
Yes. Short answer, yes. If it's part of a treatment train, obviously you don't want to recirculate back into that water back into the system. It's what we call an end of pipe treatment. So at the outflow, you don't see that water going back. But yeah, you can use it. You can use many types of flocculants and coagulants to remove phosphates from the water. Some process that I would love to try is creating a close to a Bardenfo process. You create a bacterial bloom where bacteria take the phosphate, the dissolved phosphate, out of the water, and then you can grab that bacteria, remove it out of the water, and then take everything out. It's something that we're still working on.
Thank you very much. Thank you, Carlos, for joining us.
Thank you,
everybody, for listening, and we see each other in 14 days again, and you get the email from me with the homework. Thank you, and have a nice rest of the week. Bye-bye.
Bye.